Hello everyone. So in this particular lecture number 4, we are going to see assembly of 1D element exercise. Okay. In last video number 3, we have discussed in detail on this assembly of 1D elements. Okay. So I'll just quickly recap what we have discussed in overview. Okay, so we have said that no, given assembly, okay, given a structure, when we discretize it into number of finite elements, okay, for example, let's discretize it into n number of elements, n finite elements. Okay, what are the steps, okay, to solve FEA problem? So I'll just quickly summarize it. First is the discretization. Okay, so we discretize the domain into finite elements. Okay, second step is write down FEA level element level FEA algebraic equations for each element. Okay, so writing FEA equations for each element. So what does it mean? We'll write no element level equations for all n number of elements. Okay, third is we'll do assembly of elements. So we'll perform assembly of FEA algebraic equations from coming from n number of elements. Okay, by doing so, what we'll get the global system of equations. Global system of equations. Okay, and once we get a global system of equations that we said no, which looks very same, which looks very similar to element level equations. Okay, and this is a global stiffness matrix. This is a displacement vector, and F is force vector. Okay, so this is a recap of the last video. Okay, so we have also seen we have given one exercise for practice. Okay, I'll try to give the solution for that. So I will not solve completely, but I will just give the hints. Okay, so let me open that. I'll just copy this. Okay, so this was our problem. Okay, so we have this kind of structure, okay, with L1 and L2 length. Okay, and we have defined all the inputs K1, K2, L1, L2, A1, A2, and we are applying uh, 10 kilonewton at one end of the structure, whereas one end of the structure is fixed. Okay, and unit system we are going to follow is this one. Okay, we are going to follow Newton mm turns second. So all the dimensions, all other values, we have to convert it into consistent unit of consistent units. Okay, okay, so here we have shown two problems. I will just show you the problem solution for this second problem. So first will be easy to you can easily solve this first problem. Okay, so we have a no radius of the shaft R1 and R2, lengths are given. Okay. So first thing we want to do is we want to let's rewrite this. Okay, so this is L1 length, okay, and this is L2 length. Okay, we are discretize it into two number of elements. Each length we are discretize it into two number of elements, finite elements. Okay, and we are applying force of 10 kilonewton here. Okay, so I'll just put a big dot here. Okay, and let's take this is node 1, node 2, node 3, okay, node 4, and node number 5. Okay, and the stiffness for this is k1. These are elements, element number 1, 2, 3, and 4. So 4 number of elements and 5 nodes. Okay, so stiffness matrix for each of these elements is k1, k2, k3, and k4. Okay, so length for this element is going to be uh, 0.5 meter. Okay, so it is 500 mm. Now this element is half. Okay, so 500 divided by 2. This is also 500 divided by 2. This element length is going to be 250 mm by 2. Similarly, this one 250 mm by 2. Okay, so these are the given values. The first thing we have to do is we will find the k1, k2, k3, and k4. Okay, so k1 is equal to, as we know, a1 e. Okay, we will assume I think we did not give the last time the Young's modulus, but you could have assumed. We'll say e1 equal to e2 is equal to e, which is nothing but we'll assume it is aluminum material, so 70,000 megapascal. Okay, so a1 e by l1, 1 minus 1 minus 1. Okay, so a1 is no, I have already calculated a1, which is nothing but 1962.5 mm square. 1962.5 mm square into 70,000 divided by length of this element 1, which is 500 divided by 2. Okay, and 1 minus 1 minus 1. So this matrix will be, the value is going to be 549360. I have already calculated this. So 1 minus 1 minus 1, 1. Okay, so this is nothing but k1 minus k1 minus k1 k1. Okay, then as you say, k1 and k2 both this element 1 and element 2. Okay, element 1 and element 2 are of same dimensions, okay, and same material. So we will say k1 is equal to k2. Similarly, k3 is equal to k4. Okay, so we'll get the values for k3 equal to k4 is equal to a3 e by l3, 1 minus 1 minus 1 1. Okay, a2 is going to be pi r2 square, which is 7850, I think. Okay, I remember 70,000 divided by L3 is element length 3. Okay, so element 3 length, okay, this one, 250 divided by 2. Okay, so 250 divided by 2. Okay, okay, and this value is let me check, it is 4396 triple 0 1 minus 1 minus 1. Okay, so we have got element stiffness matrix for all four elements. Okay, k1, k2, k3, and k4. Now we will write a global system of equations. Okay, global system of equations. So first we'll write a global force vector. Okay, so I'll just say global system of equations. Okay, for this particular given problem. Okay, so element so node 3, node 2 is shared between element 1 and 2. Similarly, node 3 is shared between k2 and k3 elements. Node 4 is shared between element 3 and 4. Okay, so I can write the global system of equations. Okay, first I'll write force vector F1, F2, F3, F4, F5. Okay, this is going to be a 5 by 1 because 5 number of nodes and each node has 1 degree of freedom. So this will become 5 degree of freedom system. Okay, and k by k matrix is also going to be 5 by 5. So this is k1 minus k1 minus k1 and k1. Okay, so node 2 is shared between two elements. So I will say k1 plus k2 minus k2 minus k2 k2. Okay, similarly k3 minus k3 minus k3 and k3. I will just remove this. Okay, k3 minus k3 plus k3. Okay, k4 minus k4 minus k4 and k4. Remaining terms will be 0. Okay, and I can similarly say u1, u2, u3, u4 and u5. Okay, so this is my global system of equations. Now what next? Okay, so we'll if you see the steps, once we get global system of equations here, okay, we apply the loads and boundary conditions, loads and boundary conditions, and we solve the problem. Okay, so these are the steps. So let's apply the loads and boundary condition. Okay, like loads and boundary conditions. Okay, so uh, let me write down. Okay, f1 sorry, force vector. So this problem node 5. Okay, this is one end we are applying 10 kilonewton. So external force is applied at node 5. So we'll say Fi is going to be 10,000 newton. Okay, and if you see F4, F3 and F2, they are not given any forces. Okay, external forces. So F2, F3 and F4 is 0. Okay, similarly F1. Okay, F1 is actually F1 we are not applying any external force, but it is constrained. Okay, so there will be a reaction force at F1. Okay, so wherever there is a constraint or boundary condition, in that particular degree of freedom we get a reaction force. Okay, so we will say here reaction force which is unknown. Okay, so you might ask what about 2 3 4? They might also get reaction force, right? The thing is node 2. Okay, for example, if we take node 2, okay, it is shared by these two elements. Okay, uh, so when we consider these two elements separately, node 2 uh, will have a force. Okay, but when we combine these two elements k1 and k2, okay, both the forces will cancel each other because they are in opposite so that way there is no force at node 2. Okay, external force I mean. Okay, so there can be an internal force. Okay, that is not part of discussion now, but external force is 0. Okay, this also 0 and this also 0. So F1, which is reaction force at node 2 because it is node 1, is unknown because it is constrained, and Fi is known. Okay, this is unknown. So force vector, then k1 k matrix, we can easily substitute these values. Okay, we have got these values k1 k2 k3 k4. Okay, so I'm not writing here, but we can put. Now displacement vector. Okay, as you say node 1 is fixed, so this is u1 is going to be a 0. Okay, and remaining all the nodes are free, so we'll say all are unknown. Okay, so this is our after applying loads and boundary conditions, these are our global system of equations. Okay, if we just solve this matrix, okay, or if we solve this you know, using linear algebra, okay, computer solves in a different way. I mean, computer has solvers. Okay, any program, if you take a python or any other program, they will have linear solvers, so they can easily solve this system of equations. But if we want to do with hand calculation, uh, for big degree of freedom system of equation, we cannot solve it with by hands, right? But since this is five equations and five unknowns, we can easily solve this problem. Five equations and five unknowns. What are five unknowns? So reaction force at node 1 and node 2, node 3, node 4 and node 5 displacements. Okay, so these are unknown. So we can solve this problem, okay, with the five equations and five unknowns. So that is how no this is a very broad overview of FEA equations and solving FEA problem for a assembly. Okay, when we discretize it into uh, n number of finite elements. So this we have taken with the five number of finite elements. Sorry, four number of finite elements. So this is how you solve. And so hope this is clear, and the big picture of FEA or solution of FEA is clear. So see you in next video. Thank you.